Sorry for the late start, guys. Let's see. Okay, just give me 1 second. Okie dokie. How's everybody doing? Okay, good morning, okay. Franklin, you're in the dark today. I can barely see you. Are you taking notes by flashlight? Let's see. Okay, so again, I was just a little bit behind from last week's step still, so just playing one last catch up on last week's work, and then the rest of the week we will be on this week's notes. So today is chapter 37, so let's do that. Oops. Green. Okay. So a little side note about our notes and the notes that were assigned for chapter 37. What I'm not going to go over today is a bunch of stuff about the food chain and trophic pyramids, because we kind of already did that in our Zoom session with the whole class last Wednesday. And then not for nothing, you guys had your Patrice assignment on this already. So you're already done as far as being assessed for it and stuff. So I'm skipping these sections for our notes since we're basically done in this spot. Okie dokie, so we're gonna start with species diversity. And species diversity can be split up into two main requirements or measurements, so to speak. So it's species richness and species evenness. And richness of a species, or richness of an environment or a community is the number of different species there are. Whereas evenness pertains to the proportion of those species, or if all those species are proportionally represented. So we're gonna kind of set this up in an example, and this is not the first or the last example you will do in the next couple days, because I think a couple of the videos that I assigned, really dive into this, and so does I think it's your biointeractive, or one of the cons this week, goes deep into this idea of richness versus evenness, and then how that creates species diversity. And then on top of that, this will also be the main concept you'll use for your Patrice Padlet this week. So a good one to know. So we're just going to do a really gentle example. Probably have already read through this and totally get it, but let's just do it together for good measure. Okay, so in lot A, we have a species that is called circle. Also in lot A, we have a species called triangle. We also have species called square and species called star. So don't overthink it. How many of species circle are there?
10.
Great. How many of species triangle are there?
2.
Great. And species square?
1.
And species star?
1.
Total number of all organisms in lot A?
13.
I didn't quite hear you.
14.
Perfect, thank you. Okay, in lot B, we have species circle, we have species triangle, we have species square, and we have species star. How many of circle are there?
5.
Mhm.
5.
Thank you. Triangle?
4.
Square?
2.
And star.
3.
Great. Total?
14.
Well, great. Awesome. So I apologize if this is a little like boring and too easy, but it's just good to go over because again, you will need this for your assignment this week. Okay, so between lot A and lot B, you can see that the richness is determined by how many species there are. And in both cases, there are 4 species and a total of 14. So richness is good. You would think that they're kind of even, except for when you look at evenness, in lot A, there are way more circles than there are stars, squares, and triangles. Whereas in lot B, it's a little bit more evened out. So just by looking at this particular example, you can easily say that lot B is more diverse because their totals are even, so you can directly compare these numbers. But there's more evenness between the species, therefore making it more diverse. Everyone's okay with that, yeah? Now this, when you can just eyeball it like this, it makes it super easy. But in some populations, it becomes much more challenging because you've got way more species to work with. You've got so much more diversity between species. There's so many similar numbers that are so close it's hard to tell. So scientists have come up with a way to calculate actual diversity of an area and give it a numerical value so that we may quantify diversity. And that is called the Simpson Diversity Index. They do not go over this in the book, but they do in a couple of the, or one of the cons. And again, you will need this for your Patrice this week. So important to make a note of these. So the Simpson Diversity Index is a crazy calculation. It looks like this. D is equal to 1 minus the sum of n over n squared. Where little n is equal to the total number of types of species. And big N is equal to the total number of all species. I'm just going to write in parentheses organisms. Because the two, I mean, it feels very much the same. So little n is how many different species are we talking about here? Okay, we're talking about circle, triangle, square, and star. So little n in this particular example is like 4, whereas big N is the total number of all species of organisms, which is 14. Oops. Oh, I'm sorry, little n, excuse me, I misspoke. Little n is like these individual numbers. Where big N is the number of them. There are 4 of them.
Would you add all of the, like the 5 and the 4 and the 2 together to get the little n?
Yes, after you divide them and square them. So we'll do this one together. So, for example, let's just look at column A or block A first. So for A, if we plug in 1 minus, and we're going to take a sum. So let's do all of them in this. So we're going to have, the first one will be for circles, triangles, squares, stars. Well, that's going to be too close together. So the first one for circles is 10 over 4. Squared. Squares is going to be 1 over 4, and stars is also 1 over 4. I'm doing this problem with you too. I just made this up, so we'll see how it goes. So I'm typing into my calculator all my small fractions and squaring them first. So 10 divided by 4.
Are the 2 1/4 supposed to be added, or are they going to get multiplied together?
Nope, you're right. Thank you for that. They are added together. So this is 6.25. 0.25. 0.0625 and 0.0625. Please holler at me and check my math if I'm doing something wrong. Although I think I already figured out my mistake, but I'm going to keep going for a second more. Yeah, no, I'm not. Stop, immediately stop. I figured it out. Figure out where we went wrong, or where I went wrong, excuse me. Okay, so I just need to clean up this language because I think that's what's a little bit confusing for me. Okay, when we're looking back up here, can you see my little pencil when I'm circling like that? No. Oh, you can? Oh, what do you know? When we're looking back up here, little n is equal to the total number of types of species. We need to change this wording because this is right. Total number of, let's make this wording members of each species. Does that make more sense? I just want to make this wording super clear. And we did that right. Those numbers are totally fine. That's our 10, 2, 1, and 1. But our big N, total number of all species, organisms, that's correct. I really don't even like species because that's confusing. Because this should not be 4, this should be 14. So all of these should be 14s, and that's going to change things. Where's Miss McCann when you need her? Have you guys had some Zoom sessions with Miss McCann yet? Anybody?
I have. She told us she adopted a dog.
Yes. Oh my gosh, Mr. Bubbles.
Yeah, he's really cute.
He is so cute. So cute. He's just the sweetest little love too. He doesn't do anything. Just hangs out like a little slug all day with her. So I'm just doing all this math over again, guys. Join me if you'd like. Hopefully I'm doing a better job at it this time. Am I setting this up nice like a math problem, like a math teacher would? I hope so. I'm really trying. Hooray. That's correct. Okay, did everyone else get this? Did everyone else get the diversity for block A is 0.46? Or did anyone not get that? Oh boy. Okay, well, that's what we're going with. I think that's right. I'm confident. Okay, so let's do block B, or feel free to do it on your own and just ignore me. I'm gonna write it out just like I did before. I'll do 5 divided by 14 squared. Your numbers might be slightly off from mine if you're rounding differently than I am. I don't think it matters that much, especially with this particular example. Okay, talk to me. Anyone finishing it up or get something close to that? Oh, stuff in the chat. I didn't even realize. Holy mustard. How do we go there? Oh, can I chat? Oh, look at that. That's incredible. Do you guys see that right now in the middle or just me? Okay, I'm a little confused about the Simpsons diversity index equation. On Khan Academy, the equation is D equals 1 minus the sum of n 9 n minus 1. Oh boy. Oh boy. But in the other video, it gave me the equation you just did. So is there a right equation or is it dependent on the situation or do you do both? Do both work? Thanks. Oh, Moira, you're, okay, so I'm gonna look at this one in the Khan Academy that you're talking about, Moira, because yeah, that seems very confusing. I'm not really sure what n9, n minus 1 mean, if that means like n to the 9th, or if that means like n times 9 times n again, I'm not really sure. So I'll look into the Khan and see what it says. But okay, so for what you actually need to know for my assignments, which is really the only thing that matters at this point, since this is not part of the AP, is to use this one, which should be the same as the video that I gave you. So, and especially for our little Patrice project and for what we're doing, because we're not dealing with massive numbers, I'm guessing maybe that's why. but I'm not sure. Again, I'll look into this, Moira, and get back to you on that. Kyle said, sorry, I couldn't make it today. No worries. And Moira said the 9 was a typo. Oh, I see. So it's just sum of n minus 1 divided by n times n minus 1 or something. Okay. Okay, we'll figure that out. Thank you for that. Okay, so hopefully you got numbers similar to this for plot A and plot B. And the point is that when you look at a diversity scale, it can go from anywhere between, that's an ugly 0, anywhere between 0 and 1, where 0, there is no diversity, like meaning there's just literally one species and that's it. And 1 would be infinite diversity. So you can imagine that an ecosystem on Earth, a natural ecosystem on Earth, is not going to get to either one of these points. Now, if you decided that you want to do an ant farm in a box and there's only ants in there, okay, yeah, you have 0 diversity. But I can't imagine this. I don't understand how you get to infinite. Like, how do they just keep going? But whatever, we're ignoring that. The point is that in between is where species diversity lies. So the higher or the closer you get to 1, the higher the number of Simpson diversity index that you get, the more diverse the population is. So we can clearly see that our winner for this particular example is lot B. And we knew that, we could tell just by looking, but the point is if you have a problem where it's a little bit closer together and a little bit harder to calculate, like you might with Patrice's Padlet this week, you'll have to do this calculation in order to determine which is more diverse. Okay, deep breath on Simpson's diversity index. Whew. Okie dokie. Everyone okay if I move to the next page? Super duper. Here we go. Okay, next we're going to talk about a keystone species. Oh, it's Tuesday. I can hear the street sweeper going by. I do feel bad for the poor street sweeper because he has to dodge lots of cars now. But it's nice that our city isn't doing any kind of ticketing or anything like that right now, because who's going to move their car, right? But the middle of the street is getting a nice wash that it normally doesn't. Okay, keystone species. Keystones, if you're like super into architecture, if you're making an arch, in order to make it stable, oh, I kind of messed that up. You get it. There has to be one piece in the middle that holds the other two sides up so that it makes that nice curve. We have so many of these in our beautiful school. And hopefully now, every time you walk under a beautiful arch at our school, you'll be like, ah, the keystone, perfect. But if that one particular stone is not placed there, then the whole thing just crumbles down. It's just a little bit of physics. Mr. Traber would love that. So a keystone species is a species whose presence, hey, stop it. Supports all others in the community. And the example they gave in the book was this spiny sea urchin. Whose presence seemed fundamental in the Caribbean waters. Is that how you spell Caribbean? And other than just knowing that that particular, a keystone species, is key for a population or a community within an ecosystem. There's not much more that you need to know about that, except for that when it's when a keystone species and other things are removed from an ecosystem or added to, it can help avoid or fix a disturbance. So a disturbance to an ecosystem or community, exactly what you would think. Flood, fire, drought, storm, virus. All of these things can be detrimental to a community. And if one of these things happens to wipe out the keystone species, obviously that particular ecosystem could be in jeopardy. Or if this has already happened and everything, let's say lots of things were lost, adding in this keystone species, again, can help restore the balance to it. But disturbances in general, after they happen, they can lead to ecological succession. And ecological succession is just the rebuilding of the ecosystem. And this can happen in two ways. You can have primary succession, which basically means you're starting again from scratch. Absolutely nothing was left. So by starting from scratch, technically you can make an entirely new type of ecosystem. It may not have looked exactly the same as it was before. Or you can have secondary succession, where you're starting from bare bones. And that's just like a phrase that means like from very little. Very little was left over, but because some of it was, there's more of a chance that the ecosystem will look familiar or even the same as it had before. Everybody doing okay? I have to switch to another page just because the next thing kind of has a flow to it that won't fit here. And I realize we're already at 8:35 because of my math error, but I'm going to keep going. I probably have about 10-15 minutes left. And I'll try to get done by 8:45, but if you need to go or go to another class or anything, feel free to just know that this is recording. Okay, so I'm going to another page. Okay, so we skip a bunch of stuff in the middle of this chapter, like I mentioned before, about food chain and all the different trophic levels and the energy transfer, because we kind of already talked about that, and not for nothing, we're done with that part. So skipping over a bunch of stuff and landing at invasive species. An invasive species to an ecosystem or a community means that a new species has come in that is non-native, meaning it hasn't lived there before. And this new species, when it comes in, as you can imagine, it can either be super successful and thrive and everyone likes that new species and it helps the environment, or it can be not so successful. And other species want to kick it out, or it ruins the food chain, the energy flow, and causes problems within that community. the street sweeper again. Alrighty, when we're talking about invasive species in an environment, we're talking about obviously biotic factors, right? It's a species, it's a living thing, so it's biotic. But abiotic factors can also have an influence on the balance of an environment. And this can be through a change in the nutrient resources. So nutrient resources in the environment, obviously non-living things, it can be anything from obviously the temperature and the sun and the weather and the climate, but we're focusing mainly on the chemicals, the chemical nutrients. So in this case, the specific decrease of levels of nitrogen and phosphorus. Maybe just a light bulb moment for you. That nitrogen and phosphorus are big players in the organic system. And so depletion of those, of course, are going to have a detrimental effect on living organisms. When you think of N and P, what organic molecules do you think of? I think we kind of went over these in class, but you think about your organic molecules, you've got your CHO, you've got your CHON, you've got your CHOPIN. So we know that N and P play a huge role when we come to these molecules, and that's like your DNA, RNA, amino acids. I know you're all thinking it, just didn't say it. So a decrease in the amount of nutrients or a major change that's going to mess with the nutrient levels within an ecosystem, increase or decrease, is called eutrophication. You should see embedded in this word trophic. It should give you a little hint about what happens here. And basically what happens is when you have that imbalance of nutrients, our pyramid gets super, super flat. We have way too many producers. And this can be because of humans are doing to the environment, through fertilizers, chemical runoff. But environmental changes can also be a factor. Oops. temperature change, which is different than climate change. The major point here being that humans are not doing any favors for the environment. We know that. And we are working on it. This is definitely something that is turning around. We've turned a little bit of a corner here with at least acknowledging what we're doing to our planet and now trying to make a change. So one of the big words in this century is sustainability. And sustainability just means to develop, manage, and conserve our resources. Which include all the animals. Sustainability, again, it's that new sexy word that everyone, oh, it's sustainability. Like, I have my own garden and I reuse all my plastic bottles. Exactly. In the 90s, when it wasn't quite so cool yet, it was all about recycling. And it was this symbol that looked like this. I don't know if you guys still see that around very often. But it stood for reduce, reuse, recycle. But same thing, sustainability, reduce, reuse, recycle, develop, manage, conserve, all same. If you are like me and you are constantly trying to think of a bright side to this weird situation we're in, there is very little pollution going on right now. No one's traveling, no one's on the roads, no one's driving, factories are shut down. So at least our atmosphere is feeling a little relief at the moment. It's short-lived, probably won't have any lasting effects because it's so short, but it's kind of nice. Some little bit of light there. And I'm sorry if I rushed us through that last page, but if we did get done by 8:45, hooray. Oh boy, crazy hair day. Anyone have any questions? Okay, tomorrow we do chapter 36, which is, again, we just hop all over the place. But you have all of your assignments for the week in that email and on Haiku. Just holler at me if you have any questions. Today is the last day for last week's Patrice Padlet. So just make sure you finish up your trophic pyramid and food web for her and her friends. We'll be good to go. Holler if you need anything. Oh, tomorrow morning is a little cuckoo with Zooms, right? Especially if you have me for both classes. We have our normal breakfast at Tiffany's in the morning note session from 8 to 8:45. Then we take a breath. If you're in second period, then we go into our Zoom right away at 9. But if you're in third period, your Zoom is not until 10 o'clock. Okay, so make sure that you mark your calendar for that. And if you can't come, it's okay, but it's going to be really fun because we get to do some group work tomorrow. And then if you're in Biomed 2, then you have to find your period for that because there's Zooms at 11, 12, and 1:30. Tomorrow's going to be crazy. And so on that note, I'm going to go back to bed for another 24 hours. Just kidding. All right. See you tomorrow, you guys. Thanks.